Hello guys, welcome back. I'm here with the last concept of statistics that is needed for machine learning. Up until now, we have built models, cleaned data, and made predictions. But how do we know if our model is really good? In this final episode, we'll talk about the heart of a trustworthy ML model, evaluation metrics, and statistical thinking. There are different metrics for each ML model type, but here we only cover them for classification, regression, clustering, and time series models. So the first one is classification. Let's start with a common trap, which is accuracy. If your model predicts cat every time in a dataset that's 95% cat, you'll get 95% accuracy, even though the model has no idea what a dog looks like. That's why we need smarter ways to evaluate models. Let's see the rest of evaluation metrics for classification models one by one. The first one is the confusion metrics. The confusion metrics helps us see where our model gets confused, the true and false positives and negatives. From confusion metrics, we can calculate precision, recall, F1 score, and more. Precision says that of all the things I predicted as positive, how many were actually correct positives? We calculate it by dividing true positive cases by the summation of true positives and false positives. For example, if your spam filter marks 90 emails as spam and 80 are actually spam, the precision would be 80 divided by 90 or 88%. We use this metric when we want to minimize false positives, or for this example, false spams, because we don't want to mark important emails as spam, right? And recall asks, of all the real positives, how many did I actually find? We divide true positive by true positive plus false negative. So there is a slight but important difference between precision and recall. Precision is like a sniper that hits fewer shots, but each one is accurate. However, recall is like a shotgun that hits more targets but may also miss or hit wrong ones. Let's see the same example again. We have this confusion matrix and we have true positives of 80, or our model correctly identifies 80. But this time, instead of the summation of true positive and false positive, we want the sum of true positive and false negative, or the total number of spam emails, which is 100. So we get the recall of 80%. If I want to compare these two in math terms, I would say in precision, denominator was the total number of spam emails by the filter, regardless of that if they are actually spam or not. But in recall, denominator is the actual total number of spams. These two, precision and recall, come together because they measure two sides of the same coin, or describing how well your model identifies the positive class. So to wrap up this part, precision cares about how many of your predicted positives are correct, and recall cares about how many actual positives you found. Let's move on to other metrics. The next metric is F1 score. The F1 score combines precision and recall into a single measure, a harmonic mean. It's useful when you need balance, not extremes. And real-world ML is always about trade-offs, not perfection. So here's the formula. F1 equals 2 multiplied by precision recall divided by precision plus recall. This metric balances both. It will be high only if both precision and recall are high, and it will punish models that are great at one but bad at the other one. So let's get back to our spam emails example. We had precision and recall of 88% and 80%. So F1 is 0.84 or 84%. This number is excellent and it shows almost perfect classification. Now let's get back to accuracy again. It shows the overall correctness of your model. And as I said, it is not wise to only count on it because it only shows you the accuracy of the data type that you tested it with. And if you want the accuracy for a type that the model was not fit with before, it will not help you and it can be misleading. But for our example, let's assume our model was trained by enough type of data Then we want to know the accuracy of it. The formula is true positive plus true negative divided by true positive plus true negative plus false positive and plus false negative. We do the calculation and we have 0.99 or 99% accuracy. Wow, this is very high. So let's move on to the rest of them. There are two other common metrics for evaluating classification models. They are pretty advanced and may be suited best for when you need higher level evaluation, especially for probabilistic models. So let's just learn them. First one is ROC AUC. It measures how well the model can separate positive and negative classes across all possible classification thresholds. The ROC curve plots true positive rate, which is recall, and false positive rate for every possible threshold from 0 to 1. You see it here? So instead of picking a fixed threshold, like for example 0.5, you check performance across all possible cutoffs. And the IUC area under the curve is a single summary number between 0 and 1 that measures the area under that ROC curve. The more IUC is closer to 1, the better the model is. And it shows perfect separation, meaning that the model ranks all positive above all negatives. IUC of 0.5 shows random guessing, and IUC less than 0.5 is even worse than random. It shows reversed labels. From the probabilistic point of view, IUC is the probability that a randomly chosen positive sample has a higher predicted score than a randomly chosen negative sample. And finally, the last metric is LogLoss, which measures how confident and correct the model's predicted probabilities are. Lower LogLoss shows better model, and 0 is actually a perfect model. Larger LogLoss is worse, especially if model is confidently wrong. So we're done with classification. Let's go beyond it and see some regressions evaluation metrics. In regression tasks, we use different tools. First one is mean squared error, or MSE. It measures the average squared differences between the model's predicted value and the actual or true values. Lower MSE shows a better model. The second one is root mean squared error, or RMSE, which measures the standard deviation of prediction errors, which gives more weight to larger errors. The third one is mean absolute error, MAE. It measures the average size of the errors, or the average distance between predicted and actual values, regardless of their direction. MAE of 0 is perfect. And the last one is R-squared, coefficient of determination. It represents how much of variance in the target variable is explained by the model. R-squared of 1 is the perfect prediction, and R-squared of 0 is no better than predicting the mean, and R-squared less than 0 is worse than predicting the mean. So as you saw, each of them told us how far predictions deviate from the reality in their own way. For now, we just consider mentioning them because explaining them with an example needs another whole tutorial. Let's move on to clustering. There are 3 key evaluation metrics for clustering models, which each captures a different perspective on how good your clusters are. The first one is silhouette score, which is an internal metric and doesn't need true labels. It measures how well each point fits within the assigned cluster compared to other clusters. So a score of -1 is very bad, shows that point assigned to a wrong cluster. 0 is ambiguous, which means it's between clusters, and 1 is very good, which shows point tightly in its cluster and far from the wrong ones. The second one is adjusted rand index, or ARI. It's an external metric and requires true labels. This metric measures how similar the clustering is to the true class labels by adjusting for chance agreement. So ARI of 1 shows perfect clustering, 0 is random clustering, and negative is even worse than random. And the last one is normalized mutual information, or NMI. It's an also external metric, And it uses information theory to measure how much information the predicted clusters share with the true labels. NMI ranges from 0 to 1, with 0 showing no shared information, completely unrelated, and 1 shows a perfect match. So we're done with clustering. Now let's see what the evaluation metrics are for time series models. Like clustering models, there are 3 key evaluation metrics for time series forecasting. They all measure how close your predicted values are to the actual observed values. But each of them does it in a different way and suits different context. The first one is MAPE, mean absolute percentage error. It measures the average percentage error between predicted and actual values. It tells you, on average, how far off your predictions are in percentage terms. For interpreting it, 0% says the forecast is perfect, but for example, 5% shows on average 5% deviation from the true values. The next one is RMSE, root mean squared error. RMSE measures the average magnitude of error in the same units as the data is, giving more weight to large errors. The lower RMSE, the better predictions are, and it is also sensitive to large deviations. So, for example, outliers increase RMSE a lot. And finally, MASE, mean absolute scale error, which compares your forecasting accuracy to a naive baseline forecast to make it scale-free and robust. MASE of 1 is as good as the naive forecast. MASE less than 1 is better than naive, and MASE greater than 1 is worse than naive. That was time series evaluation metrics. So far, we talked about evaluation metrics for classification, regression, clustering, and time series. There are also other types of metrics like ranking, information retrieval, probabilistic, generative, fairness and robustness, and model efficiency. But for the sake of keeping this video at an average length, and also make it more beginner-friendly, we stick to the 5 former types. Another important aspect that we need to look at and mention again is that model evaluation metrics provide concise summaries of predictive performance. However, these metrics are not fixed properties of a model. They are estimates based on a particular data sample used for evaluation. So, any data set represents only one realization of the underlying population, and the computed performance will vary if the evaluation were repeated with new data. So, to account for this uncertainty, confidence intervals can be reported alongside point estimates. Confidence intervals indicates the range that the true performance likely falls. For example, an accuracy of 0.87 with a 95% confidence interval of 0.84 and 0.9 shows both the central estimate and its uncertainty. It says if I repeated this evaluation many times on different random samples, about 95% of the intervals I compute would contain the true accuracy. You can say accuracy equals 0.87 plus or minus 0.03. This is a 95% confidence interval. And furthermore, when comparing competing models, statistical significant tests such as t-test or bootstrap tests on cross-validated scores can reveal whether apparent performance differences are genuine or merely due to chance. For example, if you want to compare two models, say Model A with accuracy of 0.87 and Model B with accuracy of 0.89, you might ask, is B actually better, or could this difference just be random? This is where we use significance testing. And at the end, this is where statistical thinking reminds us every data set is a sample, every metric has uncertainty, and every conclusion must be validated. This mindset turns you from a coder into a true machine learning scientist. And that's it. It was the last concept of statistics for machine learning that we just finished. Now, by the end of these 9 episodes, you know everything about the statistics that is needed for machine learning. In the next video, we have a bonus recap about everything that we have covered so far. So as always, thanks for watching. And if you have any questions, please ask me in the comments section. And I'll see you in the next one.